The first thing we're going to investigate of carbonyl compounds in this chapter deals with their acidity. Now we've seen that carbonyl compounds act as electrophiles, but they can also behave as proton donors, hence the definition of the Bronsted acid as well. And we're going to explore the various types of carbonyl compounds and see how they are acidic. So the first carbonyl compound we're going to look at are ketones and aldehydes. Now ketones and aldehydes have a pKa value that are typically in the high teens. We can see this with acetaldehyde. So if I determine the pKa of acetaldehyde, I see that it has a pKa of 16.7. Likewise, acetone, so dimethylketone, or 2-propanone, has a pKa of 19.3. So you see that both of these are typically in the high teens, between 16 and 19 as a pKa. And therefore, they're a little less acidic than alcohols, but depending on what else is attached to them, they can actually be even more acidic. We're going to look at some examples of that in just a moment. So let's take a look at butanal and see where the acidic hydrogen is actually located. If I take butanal and I react it with a base, it actually abstracts a hydrogen on the alpha carbon. So we talked about this in the previous section, where alpha hydrogens are the acidic hydrogens. And the reason for this, so let me draw the structure here. This is the enolate ion, and that enolate ion can be stabilized through resonance. And so when we look at the resonance structure of this, we see that there are two contributing resonance structures of the enolate ion, one that has a negative charge on the carbon, the other that has the negative charge on the oxygen. And it's actually been determined through molecular orbital calculations that the highest occupied molecular orbital actually has greater electron density on the carbon. We're going to see how that plays out later on, but that is something important to understand. Now, the key though is that we have a resonance stabilized enolate, and because of this stable conjugate base, that increases the acidity of what we would think of as a typical sp3 carbon that we would assume has an behavior like an alkane, but in fact it does not. So the key is that a carbon attached to a carbonyl has fairly acidic hydrogens because of the resonance stabilization of its conjugate base, the enolate. All right, so now the enolate ion can actually reprotonate at either the oxygen, which makes an enol, or it can protonate at the carbon, which then converts it back to the carbonyl. So let's take a look at both of those scenarios. If I simply draw out the two resonance structures of my enolate ion, one where the negative charge is on the alpha carbon, the other where the negative charge is on the oxygen. So I can protonate either one of these to get back to a neutral species. And if I protonate the resonance structure on the left, I can use water to do this. If I'm in basic conditions, and if I'm in acidic conditions, we'll take a look at that scenario as well. But in basic conditions, water can reprotonate the enolate, and I regenerate the carbonyl. So I regenerate butanal in this process. But the key is that I'm making the carbonyl compound back if I protonate that carbon. Now, on the other hand, if I protonate the oxygen, so when the oxygen has a negative charge that's associated with it, and again I'm going to use water to do this, I protonate the oxygen, and I generate again a neutral species, but now that oxygen has a proton associated with it, and so this is called the enol. And so I have a carbonyl enol, um, two possible structures that I can form once I deprotonate and then reprotonate. So this means that in aqueous base, carbonyl compounds are in equilibrium with their enol forms. And therefore, we can show an equilibrium between the carbonyl compound and the enol. So keep in mind, in aqueous basic conditions, I have an equilibrium that exists between the carbonyl compound and its enol. Okay, so let's take a look at the overall mechanism. We've seen the mechanism in pieces, and I just want to show you the complete mechanism, so you can kind of see the process of going from the the keto form to the enol form. So here I have acetaldehyde. In aqueous basic conditions, I have hydroxide. The hydroxide removes an alpha hydrogen, and the electrons go to the carbon. So now that enolate is going to be resonance stabilized to put the negative charge on the oxygen. So I have these two resonance structures, one where the negative charge is on the carbon, the other where the negative charge is on the oxygen. And now I can protonate with water and generate my enol. So I'm going from the keto version of an aldehyde to the enol version of the aldehyde. And this is called tautomerization, and it is an equilibrium, and it typically favors the keto form. So keto coming from the ketone, but if we're talking about an aldehyde, it would favor the aldehyde form. So if we're talking about acetaldehyde, it's in equilibrium in basic conditions with its enol form. Now notice that I have the equilibrium arrows, and those that the arrow pointing to the left is bigger than the arrow pointing to the right, and that's because there's actually very little of the enol present. As a matter of fact, we can measure the amount, and the K, the equilibrium constant for this equilibrium, is 6 times 10 to the minus 7th, which means that for every one acetaldehyde, I have 6 times 10 to the minus 7th of the enol. So a very small amount of enol present. And as a matter of fact, if I compare that to acetone, acetone's equilibrium with its enol is even smaller, and the K for that is 5 times 10 to the minus 9th. Now, this equilibrium can also happen in aqueous acidic conditions. And we can show the mechanism of that reaction, where here again I'm using acetaldehyde, and so now instead of basic conditions I have aqueous conditions, so I'm going to use the hydronium ion, and the first step in acidic conditions is proton transfer. So I protonate the carbonyl oxygen. So I'm showing that protonated version of the oxygen, and now what's happening is that carbonyl is withdrawing more electron density away from the alpha carbon, increasing the acidity of the hydrogen. So I can use water now to remove that acidic alpha hydrogen, and I form the enol. Right? So now notice in basic conditions I form the enolate, and then the enolate gets protonated. In acidic conditions I never form an enolate. I protonate the carbonyl oxygen, and then I form the enol from that. And so of course this is in equilibrium, so I can go reverse. I can go backwards to make my aldehyde, my acetaldehyde, so we can show that relatively easy. And the way that you show the reverse of that is that you now are going to protonate the enol. And it's the alkene portion of the enol that gets protonated. So I donate my pi electron to protonate, and I end up with a cation, just like we saw, the alkenes react with acids to give carbocations. We form a carbocation here. But this carbocation is in resonance, in which I can donate a pair of electrons from the oxygen to stabilize that carbocation and get another resonance structure, which is actually more stable than the resonance structure on the right. So the resonance structure on the left, all of the atoms have an octet of electrons, and therefore it's the major resonance contributor. And now if you notice, all I have to do is deprotonate the carbonyl oxygen, and I regenerate my acetaldehyde. And so you notice that in both basic and aqueous conditions, the product is the same, in which I go from, in this case, acetaldehyde to its enol form, and then I can go back to the aldehyde form, the enol or keto form, keto-enol tautomerism. Now, there are situations where the enol form can actually be more favored, and that is with beta diketones. So a beta diketone is when you have two carbonyls, and the carbonyls are beta to one another. So remember, if I'm looking at the carbonyl on the right, the carbon attached to it with the two hydrogens is the alpha carbon, and then the carbon attached to that is the beta carbon. So it's called a beta diketone. And so if I think about the equilibrium between the beta diketone and its enol, you see in the, I'm drawing the equilibrium arrows where the larger arrow is pointing to the enol. And as a matter of fact, so if you remember with ketones, the typical equilibrium constant somewhere around 10 to the minus ninth. For this, the equilibrium constant is 3.2. And so you see that in equilibrium, you actually have more enol than you do beta diketone. And there are a couple of other examples of this. One of them is where I have, this is called a beta keto ester. So you see that on the left-hand side, we have an ester and then a beta keto group. So it's called a beta keto ester. And this is also in equilibrium with its enol. And the equilibrium isn't quite as high as that of beta diketones. You see that the equilibrium constant is 0.1, but it's still a lot higher than the typical ketones. Now the reason for the K not being quite as high as with beta diketones is because the ester actually, that oxygen can donate electron density, and so the acidity of those hydrogens is not as great as the acidity of the hydrogens of beta diketones. Now, one of the reasons, you might be thinking, well, why is it in this particular case that a beta diketone is favored? All right, so always ask yourself, why? And the reason for this is actually relatively simple. It has to do with hydrogen bonding. So if I redraw that enol version of my beta diketone, and you notice that the hydrogen, so that oxygen-hydrogen bond is free to rotate, and that hydrogen can actually approach the carbonyl oxygen. And when it does so, it can form a hydrogen bond. And that hydrogen bond actually stabilizes the enol formation. Okay, now there are also enolates of acid derivatives. And so what we're going to see is that hydrogens in the alpha position of acid derivatives are also acidic for the same reason as aldehydes and ketones. So just to kind of review and refresh your memory. I know we just saw this, but it's always good practice to draw the the enolates. If I take, if you recall, taking an aldehyde, acetaldehyde, reacting it with a base, the base is going to remove that alpha hydrogen, and I generate an enolate where the negative charge is on the carbon. And of course, I can draw a resonance structure in which I donate the pair of electrons to the carbonyl, displacing the carbon-oxygen bond, and I form another resonance contributor where the negative charge is on the oxygen. And so we've already taken a look at this in basic conditions, right? A ketone or aldehyde can form an enolate. So if I compare this to an ester, so here I have methyl acetate. So if we think about esters and amides, they also have alpha carbons and therefore also potentially have alpha hydrogens associated with them. And if I react those alpha hydrogens with a base, I can abstract that hydrogen and I can draw a resonance structure. Again, an enolate of my ester. And in that enolate, I can draw a resonance structure to stabilize it, donating the pair of electrons into the carbonyl and then breaking that carbon-oxygen bond and placing the negative charge on the oxygen, right? And likewise, I can do the same thing with amides. Here I have acetamide, reacting it with a base, removing that alpha hydrogen, placing the negative charge on the alpha carbon, so I form my enolate, and it can be stabilized through resonance, placing the negative charge on the oxygen. So you see that the pattern is the same. I can do this with aldehydes, I can do this with ketones, I could do this with esters and amides, so carboxylic acid derivatives as well. Now, remember, though, that esters and amides are stabilized through resonance. So if you recall from previous chapters, we talked about the resonance stabilization of esters and amides in that the heteroatom, in this case for an ester, the oxygen, can help to stabilize the carbonyl. Remember, we can draw a resonance structure of the carbonyl, placing a negative charge on the oxygen and a positive charge on the carbon. And depending on the groups attached to that carbon, if we're talking about aldehydes or ketones, there is no resonance stabilization. But when we talk about esters and amides, that heteroatom can donate a pair of electrons, and we can form in this case, a third resonance structure of the ester, where the positive charge is on the oxygen. So we're taking the positive charge away from the carbon of the carbonyl, right? Now, what does this do to the acidic nature of esters and amides relative to that of ketones and aldehydes? Well, since it increases electron density to the carbonyl carbon, it's going to decrease the acidity, because remember, acidity can be increased by withdrawing electron density away from that carbon. So in this case, we're donating electron density, so we're actually decreasing acidity. And we can show this by looking at a series of simple aldehydes, ketones, esters, and amides. So here I have acetaldehyde. We know the pK of acetaldehyde 16.7. We've already seen acetone, ketone, has a pKa of 19.3, so we've already talked about those two. And how does an ester and an amide compare to the pK of these? We see these have pKs in the high teens, but when you get into esters, so here I have ethyl acetate. Ethyl acetate has a pK of 24, so it's quite a bit higher than that of aldehydes and ketones, which means it's a lot less acidic than aldehydes and ketones. And amides also are even less acidic than esters are. And so you see amides have pKs around 25. Now, there's also another issue with amides, and that is that the alpha hydrogen on the amide nitrogen is actually more acidic than the alpha hydrogen on the carbon. and in basic conditions, it's removed more easily. So, for example, just to kind of clarify, we're talking about alpha hydrogens on the nitrogen, alpha hydrogens on the carbon. Here we have acetamide, and of course it has an alpha carbon, and it also has an alpha nitrogen. And therefore it has alpha hydrogens on a carbon and alpha hydrogens on a nitrogen. Now it happens that the pKa we saw of the alpha hydrogen on the carbon is 25, but the pKa of the alpha hydrogen on the alpha nitrogen is actually 18. So it's much more acidic than that of the alpha hydrogen on the carbon. And therefore, if we react this with a base, we simply are going to remove that hydrogen and generate an anion on the nitrogen. And of course, we can draw a resonance structure to stabilize that anion, donating a pair of electrons to the carbonyl, and we form this species, right? So notice what we're doing. We're donating electron density to that carbonyl and placing a negative charge in its proximity. And so this decreases the acidity of that carbon even further. So once we deprotonate the nitrogen, then the alpha carbons on the, or alpha hydrogens on the carbon actually become even less acidic. Because of this, there is no substantial chemistry of amide enolates, and that's nice to know. But there is some chemistry of ester enolates, and so we're going to explore the chemistry of enolates of aldehydes, ketones, and esters.